I now have a stereo question for a well-calibrated stereo rig. We're given two pinhole cameras whose displacement is B, and we observe a point out in the scene, and the distance of this point to the image plane is uppercaps Z. Our cameras have a focal length of f, and of course this point is being projected into two different locations for the two different images, x2 and x1, and for the sake of this question, we're going to just consider delta x, which is x2 minus x1, the displacement in the corresponding images. I will measure delta x in millimeters, same with the focal length f. B is in meters, and so is z. And I use meters for B and Z so that the units effectively fall out. You don't really have to consider them. But suppose the measured delta x is 4 millimeters at a focal length of 40 and our displacement is 0.1. How far away is the object in meters? Suppose we have a displacement of 0.05 millimeters for a focal length of 50. We now care about the baseline B, if we happen to know the object is 100 meters away. Next, we have a displacement of 0.1 millimeters. We don't know our focal length. We know that the baseline is 0.2 meters and the object is 50 meters away. And finally, we don't know the displacement, but we do know that the focal length is 200 millimeters. We have a baseline of 1 meter and the object is 50 meters away. Can you fill in the missing numbers? So we answer this question by first writing down the fundamental equation here, which is delta x over f relates to b over z. To see this, we find by equal triangles that this triangle over here, described by z over b, is the same as these two things over here put together into a single triangle, which is delta x over f. So this proportionality must be the case. This can now be transformed to resolve for z. Z equals f over delta xb. If we plug in f over delta x, we get 10 times 0.1 is 1. We can resolve it for b, delta x over f times z. We plug in delta x, 0.05, divided by 50 is 0.001 times 100 gives us 0.1. We can also resolve it for f, which is z over b times delta x. Z over b is 10 times delta x is 0.1, gives us 1 over here. And finally, we can resolve it for delta x, b over z times f. B over z is a 50th, times f is 200, gives us 4 over here. And all the units fall out by themselves. We will now talk about correspondence in stereo. You might remember our dynamic programming approach for resolving correspondence along an entire scan line. So here we have a scan line. This is the left scan line, red, red, blue, 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 red. And in the right scan line, we get to see the following. Obviously, there's a shift going on of certain sorts. I'd like to ask you where this pixel over here will go in terms of data association. It can go to any of those pixels over here, so please check exactly one of those boxes. Let's assume a cost of a bad match. When we match two colors that don't correspond, is 20. And the cost of an assumed occlusion or a disocclusion is 10. So try to find the optimal alignment and then tell me where in the right scan line this one pixel corresponds to. Check the exact box to which it corresponds. Here's a second question I'd like to ask you. What if we change the cost of occlusion to 100? Please answer the exact same question. Where does the B over here go under this different cost model? In the case where the occlusion costs are low, it is best to assume that those B's over here correspond as indicated. That means we have an occlusion cost to pay over here, an occlusion cost to pay over here. Our total cost is 20 for two occlusions, but we have a perfect match. As a result, this B moves over here. However, this is not a viable solution if the occlusion costs are large, because you would pay a total of 200 in occlusion costs. If we match pixels one on one like this, then we get two mismatches, one over here, and one over here. The cost of those in total are 40. That is still smaller than the 200 occlusion costs we had before. Therefore, the B gets matched to this point over here. Notice how the different occlusion costs give different results for the correspondence problem in this dynamic programming question. This final question is motivated by structure for motion, and is not the full-blown structure for motion problem, which is hard to do on a piece of paper here, but it's a variant of it by which I know the motion, but not the structure. Suppose we're giving two cameras, and we happen to know there's three features in the scene, and all three features can be seen by both cameras. This camera will see a feature on the left, in the center, and on the right. LCR, this is camera A, and camera B will also see a feature on the left, center, and right. But I don't know the identity of those features, which I will call 1, 2, and 3. So suppose in camera A, we see from left to right the following sequence. 1, 2, 3. These are the feature numbers. So in the left camera, we notice that the leftmost visible feature is feature 1, center feature is feature number 2, and the right feature is feature number 3. I'm going to ask, what is the order of those pixels in the camera B, assuming that the features are located as shown over here, and so are the cameras. So please give the index of the features over here. They clearly have to be 1, 2, and 3 in some order, which you have to determine. And for a different configuration, let's now assume we get to see 1, 2, and 3 in camera B, and we care about the feature indices we see in camera A that corresponds to those features over here. So let's study the first case. We saw left feature number 1. The left one is over here, therefore this will be feature number 1. Feature number 1 will be seen at the center of camera B. In the center of the left camera, we see feature number 2, which must be this guy over here because it's the center feature to be seen. This will be projected to the right side of camera B, even though it's left in the image plane. The way I drew it, you can see that the projection over here is on the right side of the camera chip. And the same with feature number 3, which is seen R over here on the right side, hence it'll project into the leftmost field over here. Using a different color now, if camera B sees feature number 1 on its L position, then this must be feature number 1, which will appear in the right position for camera A, and sees feature number 2 in the center position, this guy over here, which shows up in the left position over here, and the remaining fits in over here. So this is the correct answer. So in this question, I want to test your knowledge about the dimension of the state space of a dynamic system. In all of these questions, I'm going to look at a ball, like a soccer ball. The interesting thing about a soccer ball is its orientation is really not an important variable, whether it's upside down and so on. So in all of these questions, I'm going to exploit this, the fact that this object is rotationally invariant. So let me start with a simple question, which is the kinematic state, which is the state without any velocities of the soccer ball while it's on the ground. And I follow up with a question with the same kinematic state of the ball in midair. The difference being between these two questions that on the ground, it's confined to be in a two-dimensional ground plane, whereas in midair, we might add another dimension or not. Let's look at the dynamic state on the ground and in midair. And for the dynamic state, I wish to ignore things like spin. I just care about velocities as a person really far away could observe them, just to make things clear. And finally, I like to include spin. So let me take the most complicated situation of dynamic state in midair, considering spin. The last one is really a tricky question, so I don't mind at all if you get this wrong. But in all of those, I would like to exploit the fact that I really don't care about the absolute orientation of the soccer ball. It's a sphere, so it's invariant to its orientation, but it might still have spin. This will be a dynamic programming question for a robot with 3 coordinates, x, y, theta, even though in this diagram I just showed 2. Suppose our target location is in the top right corner facing east, as shown over here. An initial robot location is in the bottom left corner facing north. Suppose our goal is worth 100. Going straight costs us -1, and we can turn on the spot, but turning on the spot costs us -5. What will be the value of the start state? Same situation as before. We'd like to go from here to here. Give a 3-dimensional state space. Goal is worth 100. Straight motion costs -1. Turn on the spot clockwise costs -10, but turning counterclockwise, which is counterclockwise, costs us 0. What is now the value of the start state? So please put your answer in here.